So if you are doing the problems on the worksheet 7, this one is similar to the one before. The one before were inductors. This one, these are capacitors. You might notice the symbol for the capacitor is a little bit different than the way your textbook shows it. It has one little curvy line and one straight line, but that's just an alternate form for it. You'll see that in this example, all the capacitors are labeled with their voltages and their capacitance. It says, assume that the initial energy stored in the capacitors is 0. That is actually not possible. I wrote that. That can't be, because they all have a voltage, so that's just not even possible. So we'll just take that out. It doesn't matter, though, because we're just trying to find the equivalent capacitance, so it does not matter if they're charged or not to find the equivalent capacitance. So the capacitance are their farads. Now, capacitors act, the way you add them is kind of the opposite from resistors and inductors. So capacitors in parallel, so if I have two capacitors in parallel, let's see. C1 and C2, then the equivalent capacitance of those is C1 plus C2. Whereas if I have two capacitors in series, the 1 over the equivalent capacitance is 1 over C1 plus 1 over C2. Or, another way of writing that is that C equivalent is 1 over C1 plus 1 over C2. Or, if you just have two capacitors, you can use the shortcut of product over sum, C1 times C2 over C1 plus C2. But if you have more than two, then you can't use that. You would have to use something like that. Okay, so we want to find the equivalent capacitance here. So the first thing that we have to do, look and see what's in series, what's in parallel. I want to start as far away from the terminals that we are trying to find as possible. So I see right over here I have two capacitors in series, and so my equivalent capacitance for those will be product over sum, 8 times 32 over 8 plus 32. And I believe that gets me 6.4 nanofarads. So then my circuit looks like this. And so this was 6.4 nanofarads, and this was 5.6 nanofarads. Now those are in parallel, so since they're in parallel, I can just add them together. And 6.4 plus 5.6 is 12 nanofarads. And this one up here is 18 nanofarads. So now I have an 18 and a 12 in series. And since they're in series, to add them I need to do product over sum. So 18 nanofarads, so product times 12 nanofarads over 18 plus 12, and I believe that gets me 7.2. So that's these two together. That's 7.2 nanofarads. This one from the original problem was 12.8 nanofarads. Those are in parallel, so since they're in parallel, I can just add them together. So I now have 12.8 plus 7.2 is 20 nanofarads. And this is 8 nanofarads. and 10 nanofarads. No, it's not. It's 40 nanofarads. Yep. nanofarads. So I have 3 capacitors here in series, and so in order to, if I wanted to do all 3 of them at once, then I can't use product over sum. So instead, what I can do is I can say that my equivalent capacitance is 1 over 8 plus 1 over 20 plus 1 over 40, which is not so bad if you have a good enough calculator. So 1 over 1 over 40 plus 1 over 20 plus 1 over 8, and I get 5. So my equivalent capacitance is 5 nanofarads.